In this video, we're going to be doing a Unit 8 Fluids FRQ for AP Physics 1. So we have a block of mass M is attached to a vertical ideal spring of spring constant K. The block hangs vertically from a rigid support and comes to rest at an equilibrium position. The block is then pulled downward by a distance a from the equilibrium position and released from rest at time is equal to 0. Assume that the subsequent motion is simple harmonic motion and air resistance is negligible. Derive all expressions in terms of mka and g as needed. So our setup for this is going to look like this vertical spring. It's like a hangman almost setup. And then we have our spring coil like this. And then our mass is going to be attached to the spring. So what we first want to do is we are going to have a measure of displacement from an equilibrium position, which is going to be the natural resting state of the spring. So we can describe this as a restoring force. So this is going to be equal to negative kx. So this is going to give us a derivation using Newton's second law, which is m d squared x dt squared is equal to negative kx. So that means that a would be equal to negative k over mx for our simple harmonic motion. Now, for our first question, we're asked to determine the period t of the block's simple harmonic motion. So we know that when we have a mass spring oscillator, which here we do, we have our angular velocity is equal to the root of k over m. And we know that we can get period with 2 pi over omega. So then if we take omega's definition here and we substitute this in to our period, we're going to get that period is equal to 2 pi over the root of k over m. So then we can take this and we can put this into the numerator, but then we would have to flip the inside of the stuff that's underneath the radical. So that would give us 2 pi is equal to the root of m over k. So in this equation, we can see that our period is equal to this expression that does not have anything else but mass and spring constant. So these are the only two variables that are going to affect our period. So gravity and amplitude are not contributing factors to the period of a spring. So if you had a larger gravity, that would not increase your period. And if you had a larger amplitude, aka if you pulled it from a larger distance, then it would not affect the period. So amplitude is the distance that is from equilibrium position. So for our second question, we're asked at which positions does the block reach its maximum speed? Derive an expression for this maximum speed, V max. So we know that in simple harmonic motion, we have a V max when you are at your equilibrium position. That's because x will be equal to 0, and x measures your displacement. That's because when you're at your equilibrium position, that means all your energy is going to be solely kinetic, and your spring potential energy, your US, is going to be equal to 0 at that point. So then we can find the Vmax with energy. When you are at your release point, that means that your displacement from your EQM is equal to A, and your V is equal to 0. So that means all your energy when you're at your release point is equal to your spring potential energy. So you would say that's equal to 1/2 Ka squared. But when you're at equilibrium, your displacement is equal to 0, and your spring potential energy for the oscillation is equal to 0. So you can see that all your spring potential energy for the oscillation will not be here. So that's because all your energy is going to be kinetic at this point. So that means that you would have 1/2 mv squared max. So because we know we have conservation of energy on Earth and in our universe, we can set these two total energies equal to each other. So we'll set E initial equal to E final, as in E initial being equilibrium to the release point. So we would set 1/2 K A squared, and by the way, it's 1/2 K X squared, and X is your displacement. So that's why we said A there, is equal to 1/2 mv squared max. So here we can cancel out that 1/2, and we have Ka squared is equal to mv squared max.